Okay, so let's get started. As you guys hopefully have all heard by now, the homework was delayed to Thursday. I'll give you guys an extension because apparently the homework is a lot harder than we anticipated. Did everybody hear about that? Anybody not get that message? If you didn't get that message, make sure you talk to Al and get on his list so that you do get future announcements. Were there any other announcements you wanted to make? Next Tuesday. Wow. Okay. Next Tuesday. That's fine. I guess. Oh, it was. Oh, that would have been fine. Okay, that's fine. All right, that's fine. Okay, so next Tuesday. Any questions or comments? Yes.
So last few lectures we have been studying about distortion.
Mm-hmm.
So just I wanted to we have studied one method of reducing distortion, that's feedback. But other than that, does feedback, say, of a MOS amplifier depend upon its bias voltages or bias currents? So what else could we do to handle linearity?
Okay, so the question, I'll repeat it in case it didn't get recorded, is besides feedback, what can we do to reduce linearity? Well, a lot of times you're working with a single block, like let's say you're designing an amplifier or a mixer and you're trying to improve the linearity. Having an analysis tool is the first step, writing down equations that describe the distortion as a function of the device parameters. So then for a given topology you can try to optimize the performance by picking the transistor size, picking the currents, and basically if it doesn't look like it's going to work, you go with another topology. And based on experience, you tend to know what topologies are good for distortion, which topologies are not. Generally, you will use some kind of feedback to improve things. If you're designing a whole system, though, you have more flexibility. You have basically more options. You basically need to find out what's dominating the distortion, so you do a cascade analysis and try to design your overall system to get the best distortion. Now, if we have some time in this course, topic we talk about in other courses like 242 is when you design power amplifiers. There's some tricks you can play to do improve the linearity. Some of them involve doing feedback with a baseband signal as opposed to an RF signal. So you use envelope feedback mechanisms and phase feedback mechanisms. Cartesian feedback is an example. Other techniques, for instance, inject second order into the amplifier to try to cancel the third order through second order interaction. So there's some other tricks that you can use, but at some point you just have to live with the distortion that you get. Okay? Other questions? Yes?
So the next homework going after that, when is that going to be?
I don't know. We'll see. Probably a week.
Here's what happened. It's supposed to be due this coming Thursday, but many people have a midterm. And it's also a hard homework. So you don't want to be doing really hard homework while you're studying for later. Great. Okay. I agree. Move it Tuesday. But if you want to stay on schedule, we have to have the next homework still due on Thursday after that. So if you have time, as I said in the email, if you have time, do the hard homework now.
Well, why is the schedule so rigid? Why can't we? I don't care. Yeah,
we can move the next one back, but it's been running as a distortion homework, so.
Yeah, it's fine. Yeah, it's fine.
So, I'm happy with whatever, but expecting to put a post the next homework 5, this Thursday, so you'll have both there. So if you have time, try to stay on the original schedule. If you have this midterm, okay, you're just going to work hard all weekend.
Yeah, that sounds reasonable. We'll give you at least a week to do the next homework.
You'll at least a week. You'll get it early.
Yeah.
On the normal schedule. There'll be some overlap there.
Make it easy.
Fine, easy.
Okay. Any other questions or comments? Also note that homework 2, graded homework 2s are going around, so make sure you pick yours up by the end of class today. Okay, so let's start today's lecture. We're going to talk about noise, and more specifically electrical noise. I'm not going to, you might argue that every lecture so far has just been me making noise. So electrical noise. A lot of you are already familiar with electrical noise, and some of you have never really thought about it. So one way to think about electrical noise is kind of experimentally. Imagine you have an amplifier that you've built in the lab, And let's say you ground the input, so there's no signal going in, and then you look at the output on an oscilloscope or on a spectrum analyzer. And let's say it's a very sensitive oscilloscope or a nice spectrum analyzer. Well, what you'll observe is this noisy signal, this random signal here. So this is V out as a function of time, and this is noise. Okay? And one thing you'll observe is it has zero average, basically. In other words, there's a DC on here, right? That's the DC of the amplifier. But this noise signal will have no average value. And basically, it will depend a lot on how you observe it. In other words, you'll discover that if I take a cable and it's a longer cable, the noise may change. Or if I put a filter in here and look at the noise, it'll change. You'll find that the noise is very highly sensitive to how you observe it. And by observation, I mean what bandwidth over which you observe it. So we'll talk about that more. Let me just say that, first of all, that all electronic amplifiers, and more generally components, generate noise. And this noise is actually something that you have to live with. It's not something you can get rid of. It's a fact of life. It's nature. It's thermodynamics. Basically, all resistors also are noisy. And if you think back to how a resistor works, you can imagine where this noise comes from. Remember, in our simple model for a resistor, you apply a voltage or you apply an electric field and you get drift current. In reality, though, you have drift current as a small contribution to a large fluctuating current, right? So if I were to zoom into a resistor and observe somehow or another electrons, you'd find them all moving about seemingly randomly and at very high velocities, right? So they're all moving in random directions with very high velocities. The average velocity is proportional to kT, right? The average energy. So if I take 1/2 mv squared, it's going to be some fraction of kT. So it's a thermodynamic thing. And when we apply an electric field, we get a drift. We get a small motion that's proportional to the electric field, but the electrons still continue to move about seemingly randomly. In fact, it's kind of hard to even see them moving in the drift direction at all, because the drift velocity is usually much smaller than the random velocity. Okay? And because they're just moving about randomly, the potential across this resistor also varies randomly. And so you can study the statistics of that process in detail. Now, there's a couple of interesting things about this noise signal. One, we have no idea what it looks like. I can't ever predict what the noise is going to be. By definition, it's totally random. But what I can predict is its mean and its variance. So the mean is going to be 0, let's say, for a resistor. And its variance, we're going to show, is proportional to the resistance. Okay? So let me look at the noise power. So if I, first of all, take the average value of this signal in time, or if I take the average value over an ensemble of resistors, because the process is ergodic, if you know what that means, then both averages are actually equal to 0. Okay? So this is a 0 mean process. So in time, or basically, if you freeze time, for an ensemble. Now, Professor Razavi has a nice discussion about the basic properties of random signals. I encourage you guys to read that section out of his book. What we find is that the variance is non-zero. So the variance is the average of the square value. In other words, it's Vn squared t dt integrated over time. And we usually, instead of talking about the variance, we usually talk about the RMS value. The RMS value is exactly what it says it is. It's the root of the mean squared. So it's the variance square root. Okay. So most of the time, when people talk about the noise, they talk about how much noise there is. They might say there's 2 nanovolts of noise. Well, what they're talking about is, of course, is the RMS value, not the actual value of the noise, because the actual value of the noise is varying all over the place. So what you can capture is the RMS value of the noise. Okay. What about the spectrum of the noise? In other words, if I take my amplifier or my resistor and I hook it up to a spectrum analyzer, so here's a spectrum analyzer. Remember, we talked about this briefly last lecture. So this is the cable hookup. I take a resistor here, R, I just hook it up to my spectrum analyzer, and I look to see what kind of spectrum this resistor noise has. What I find is that it's flat, or what we call this white noise. And this is true for most resistors, okay? So this is the spectrum as a function of frequency. This is the frequency axis. All right? In other words, you know, plain vanilla resistor generates flat spectrum noise. So if I look at 1 hertz, let's say here, it has a certain amount of noise power associated with it. If I go to 10 kilohertz, it's the same. If I go to a gigahertz, it's the same. And in fact, if you go up to 10 gigahertz, even up to a terahertz, it's practically the same. Eventually, it starts to drop, right? Because it would be unphysical if this were flat all the way out into infinity. Eventually, it has to drop, and quantum mechanics does actually predict at what frequency it will drop. But for all practical purposes, for any electronic circuit that we deal with, this looks like it has a flat spectrum. Okay? Now, what does that mean? Well, if you're... How many of you guys have taken 126 or an equivalent like probability course? All right, so most of you guys know what we're talking about. For those of you who don't be too intimidated. You will learn this stuff eventually. But you know that the spectrum really comes from taking a transform of the autocorrelation function. In other words, the spectrum is a measure of how correlated the signal is with itself. So if you have a flat spectrum, right, that means the autocorrelation function is a delta function, meaning the signal is only correlated to itself instantaneously. If I look at the correlation, so here's a signal waveform, right? And if I examine the value at t and t plus delta, and then I take the correlation between these two signals, right? Because they're close together, you might say, maybe they're correlated, right? If this one's, let's say, 1 nanovolt, and this one's just a little bit away, maybe it's actually going to be correlated to 1 nanovolt. But you find they're totally uncorrelated. So when I take the expected value of the correlation, I get basically no correlation, that these signals are completely uncorrelated. And that's why if the autocorrelation function is a delta function, and that's why I get a flat spectrum. If this were non-flat, let's say this is another random signal, that means that indeed the signal is correlated to itself. So a later sample is correlated to the sample at one given time. So the white noise has a very interesting property that it's completely uncorrelated to itself. That means it's mathematically a very difficult signal to analyze, right? It's, you know, more, if you take a course in, let's say, 226, you realize that this is actually a Wiener process and not a hot dog, but a mathematically complicated thing that you have to learn to analyze. In this course, though, it'll be pretty easy. It's just flat. Okay? Any questions about that? All right, so let's... Yes?
So, does the fact that the noise is flat constantly against the fact that resistors are frequency
That's part of it. We'll talk about that. But it has more to do than that. It really, the shape of the spectrum really is a function of what the statistics of the signal are. So this is an arbitrary signal. It doesn't have to be a resistor, noise. This is just some random signal, and we want to know what this power spectrum looks like. Okay, so let's look at the thermal noise of a resistor. Well, I believe it was Johnson who first observed that a resistor has noise associated with it. And I think Johnson did some experiments and found that the noise is proportional to the resistance. Okay, and so some people call this Johnson noise. I think it was Nyquist who actually explained where the noise comes from. So you can also call it Nyquist noise if you like. But it doesn't matter. You can represent this noise as a voltage source in series with an ideal resistor, or a current source in parallel with an ideal conductance. And notice I draw two arrows here. You can't see that because there is no direction, right? The phase is completely arbitrary. It's noise. Sometimes it's positive, sometimes it's negative. Same thing here. If you see someone carrying around the phase of the noise, voltage, you know they're fooling themselves, because at the end of the day it doesn't really matter what phase it is. It's totally random. Okay? And so Nyquist proved, using thermodynamic arguments, that the RMS value, the variance of this noise voltage, is the famous 4kTRB. So KT, this is Boltzmann's constant. This is the temperature. This is the resistance, of course. So the bigger the resistance value, the more noise. And this is the bandwidth of observation. So if I do this experiment where I look at the amplitude of the noise, I should specify what bandwidth I'm observing. Okay, and that's a very important point that's going to come up. Now, I can also represent this as a current noise, completely the same thing. It's going to be 4kTg times B. Okay, any questions? Now this equation in some ways should be comforting because it has kT in it, right? Because we know that kT is related to thermal energy, right? It's the thermal energy associated with a degree of freedom in a system. And because this is thermal noise, this is due to the random energy that carriers have, you would expect kT to pop up somewhere. Okay. Let me talk a little bit about the spot noise. A lot of times people will talk about the noise in a narrow band. In a narrow band of interest. And so basically, if I just divide out the bandwidth, I'll call that delta F because it could be a small bandwidth, then I would just say the noise is 4kTr. But it's understood that this is the noise per unit hertz because I've divided out by the bandwidth. And if I want to get the total noise, I have to always integrate over the bandwidth of interest. If the noise is white, integration is trivial. You just multiply it by the bandwidth. Okay? So for a complicated circuit, the LC will modify noise spectrum. Okay? We'll give an example of that. Now, one thing I should mention is L and C, or ideal L's and C's, are noiseless. An ideal capacitor has no noise, an ideal inductor has no noise. Real inductors and capacitors, we know from this class, have series resistance, parallel resistance, and that will generate noise. Anytime you have a physical resistor in your circuit, it will in fact generate noise. Right, questions? Okay, let's do a quick example. Let's say that you have a 10 kilo ohm resistor and the temperature is 20 degrees, or about 293 Kelvin. So what's 4 kT? 4 kT is 1.62 times 10 to the minus 20 joules. So if I plug that in, Vn squared is going to be 1.62 times 10 to the minus 16 times the bandwidth. All right, that's just R times 4 kT. And so the RMS voltage is just square root, the root of the mean squared, and that gives us 1.27 times 10 to the minus 8 square root of bandwidth. So again, you might find somebody saying something funny like the noise voltage is 1 nanovolts per root hertz. What are they talking about? This is where the root hertz comes from, because the noise power is proportional to bandwidth. Noise voltage, therefore, is proportional to square root of bandwidth. Okay? So for example, if I make a bandwidth of 10 to the 6 megahertz, I find that the RMS voltage is 13 microvolts. 1.3. So this is actually a large enough value that you can even observe it on a scope. If you go on an oscilloscope and you put a resistor across it and make sure you're in a high input impedance mode and limit the input bandwidth, let's say it's a scope that has a natural bandwidth of about a megahertz, then you will see roughly a thick line that represents the noisy voltage, and its thickness will be roughly on the order of 10 microvolts or so. Okay? And that's a pretty sizable voltage, right? You can imagine doing an experiment or putting an antenna up in the air and picking up a voltage on the order of microvolts. So this noise actually is pretty important. It can be very important. Questions? All right, well, what about if we have more than one resistor? So let's say I have two resistors in series. Well, each one has its own voltage noise. I can put those in series, right? Say Vn1, Vn2. And so the total noise voltage across here, again, I say noise voltage, but you know what I'm talking about. It's not really a noise voltage. I'm talking about RMS values. Total variance is going to be 4 kT R1 plus R2 times B, which is Vn1 squared plus Vn2 squared. So the important point is that noise powers add, not noise voltages. Okay? If I have two resistors in parallel, R1 and R2, the total noise current is 4 kT G1 plus G2 times the bandwidth. In other words, it's IN1 squared plus IN2 squared. So again, we don't add currents, we add variances. Okay? So this is true for any pair of independent, that's the key point here, independent noise sources. And another way to say independent is zero correlation. In other words, this noise voltage is completely uncorrelated with this noise voltage. They have nothing to do with each other, and that's why their variances add. If they were correlated together, then you would imagine that sometimes they would cancel each other out, and so maybe that would reduce the variance, right? Okay, more complicated circuits, let's just say resistive circuits. Let me say I have a circuit that looks something like this: R1, R2, R3, RL. and I want to find basically the total noise voltage appearing across this resistor RL. Well, I can use circuit theory and make this a Thevenin equivalent VTS and an equivalent Thevenin equivalent noise and solve the problem. Okay? Now from circuit theory, of course, the Thevenin equivalent is equal to R3 divided by R1 plus R3, right? And the Thevenin equivalent noise is just 4kT R Thevenin times Vs here, B. So the Thevenin equivalent resistance, looking back here, is R3 in series with R1 in parallel with R2. Okay, is this right? My notes might be wrong here. So open circuit voltage should be R2, R1 plus R2. Okay? So you can use circuit theory to simplify your circuits, and the final resistance value you have, you just make sure you associate noise with that resistor, and you get the right answer. Okay? Questions? Yes.
In this expression, there's no RL, right?
This is just the noise of the source, right? So you're right. If RL is a real resistor, I have to associate VRL as well and add that. Good question. Okay, and then we can kind of generalize this. This is noise for a passive circuit. So the idea is I have this black box, and basically I just tell you this is a passive circuit. So there's L's, R's, C's, let's say ideal current sources, voltage sources, there's dependent sources, but it's passive. Okay? And let's say that at a particular terminal pair, I look in and see some impedance. Okay? Well, the nice thing is I can replace this passive noisy circuit with a passive noiseless circuit. In other words, I take this guy and just turn off all the noise sources, and I get this, and I can represent the equivalent noise as just a noise in series or a noise in shunt, depending on how you like to do things. Let's call that V equivalent. Okay? And the spot noise for V equivalent is 4kT, the real part of Z of j omega times delta omega. And if I do basically a shunt noise, I would take the real part of Y of omega, or the admittance. Okay? So this is just the spot noise. This is a noise at one particular frequency. If I want the total noise, I have to integrate over the band of interest. Okay? And now notice that the integration is not just the simple multiplication of the band times this expression, because now there's frequency dependence in Z of omega. Right? So even though the L's and C's in this circuit don't generate noise, they shape the noise. Okay? So all the noise sources could start out as being white, but they get shaped by the L's and C's in the circuit. Alright, so let's do another example. And this is one of those really important examples that will stay with you. Let's look at the noise of an RC circuit. Okay? So an RC circuit looks like that. And we want to find the equivalent noise looking into this terminal here, right? So this is going to be our black box. Well, according to what we just learned, all we have to do is calculate the impedance and take its real part and associate noise with that real part. So Z, which is 1 over Y, is 1 over G plus J omega C. If I multiply numerator and denominator by a complex conjugate, I get G minus J omega C, G squared plus omega squared C squared. Okay. So now, let me find the total noise by integrating from 0 to infinity G squared plus omega squared C squared d omega. And I'm going to introduce, instead of integrating over f, I'm going to integrate over omega and introduce a 2 pi here. Okay? So I do this integral, or I look it up in a table, and I find that I get a really simple answer. The overall noise is just kT over C. So the total noise only depends on C and the temperature. Now that's not an intuitive result, because we just said capacitors are noiseless, resistors generate noise, and yet for this circuit the total noise is independent of the value of resistance. That seems very anti-intuitive. Does anybody have an explanation? Perhaps somebody who's seen this calculation before. Anybody want to take a guess? Someone who hasn't seen it before? Okay.
If you have a bigger R, then you have more noise at first, but you also roll off a lot sooner.
That's right. So basically the effect of the bandwidth cancels out the effect of the noise. So we know the RC corner frequency for this is just RC. That's why we call it the RC corner frequency. So if I make R bigger, it seems like I have more noise, but I also have less bandwidth. So they end up canceling each other out. Very good. All right. So how about the noise of a receiving antenna? Whoops. In other words, let me just take a piece of wire like this, a dipole antenna, okay? And let me observe the voltage across here, right? And let's say I'm in a room and there's no signals being picked up. Even if I pick up signals, I'm going to ignore the signals that I pick up. I'm only interested to find what, so that basically I want to find out what's the noise that I pick up on this pair of wires. Let me tell you that these wires are ideal. And so they have no resistance. No resistance at all. So we know that this antenna will not have any physical resistance associated with it. But I find that I still pick up noise when I hook this up to my spectrum analyzer. I still find that there is noise. So if I look at the spectrum analyzer plot, I see some kind of noise floor that's higher when I hook up the antenna than when I don't. Now maybe I see a signal here, but forget the signal. Let's just focus on the noise. Where is this noise floor coming from? All right, anybody have a guess? Let me give you guys a hint. If I point my antenna to the sky, I get a different noise floor than if I point it to the ground. What is atmospheric noise? The sun? Okay. Let's say I'm in space, right, and I'm really far away from any stars, right? And I do this experiment. Will I pick up noise?
Well, it depends on how you measure the noise. Are you measuring ideally? Or?
Okay, so the question is, how do you measure? Let's say it's ideal measurement. Well, I think you guys probably have known the answer. You studied this in thermodynamics. In thermodynamics, we learned about black body radiation, right? You know that any body at temperature T radiates, right? And that's called black body radiation. So depending on where I point this antenna, like if I point it to the sky versus if I point it to the ground is pretty warm, so I'll pick up more radiation coming off the ground. So the important point is that even though there's nothing actually generating noise within the circuit, there's no resistances here, this antenna still can pick up noise. Okay. All right, so we've looked at noise due to resistors, right? We've looked at noise due to RC, LC, LCR circuits. What about active circuits? Let's look at diode noise. So diodes have what we call shot noise. Okay, and basically it's due to the quantized nature of charge. In other words, when current flows in a diode, right, we have basically carriers crossing a junction. So it's important that we outline here that you have a junction. So a voltage potential. And these carriers are not arriving uniformly, right? They're arriving randomly. It's actually a Poisson process, a random arrival time. So these charge carriers arrive randomly, and every time they arrive, you get a delta of current, right? A little delta spike of current because the charge carriers arrived. If they arrived uniformly, then when we looked at the spectrum, you would expect to see spectral peaks at all harmonics of basically the period of arrival, right? But actually they arrive randomly. So if I take into account that there's a finite amount of charge arriving, there's going to be some noise to our current, right? Because at some point there's lots of current, maybe 1 million electrons have arrived, maybe a nanosecond later only, let's say, 500,000 electrons are crossing this junction. So the amount of current is instantaneously varying, even though there's an average DC current, right? And if you do the statistics, you find that the noisy component of this current is actually proportional to the DC current, the bandwidth, and the quantum charge, right? Basically, the amount of charge that you carry. So you could think of shot noise as just being due to the lumpiness of noise. Okay. Now, there's a nice analogy for shot noise. There's actually another kind of noise that has a similar origin. It's called popcorn noise, because it's kind of like the noise that you hear when popcorn's being made, right? The pops are happening randomly, right? And so you hear these pops, and it's kind of a nice, beautiful sound. I'll give you another analogy. Imagine you're sitting reading a nice book on a rainy day, and you have a tin roof, right? So every raindrop that falls makes a little sound. And even though if you put a bucket out and you watch the water level rising, it's going to rise at more or less a constant rate, right? That's the DC current. But the water drops are arriving randomly. So they actually make also a nice sound on the roof. Kind of a noisy sound, right? And another example is snow on your television, right? You listen to a channel that doesn't exist, you hear that noisy sound. A lot of this is just related to random arrival time and the discreteness of charge. Okay? So this is the shot noise. It's very important. What we'll find is that junctions in a bipolar transistor also generate shot noise. So if I look at the base current, it also generates shot noise. And if I look at the collector current, it also generates shot noise. Okay? And these shot noises are also white. In other words, they have a flat frequency spectrum. Do you guys think these two noises are independent? Why? Yeah, it's actually, it might bother you because you might say, well, the DC current is just beta times the base current, right? Collector current. But here we're talking about two different junctions that are being crossed, and there's kind of there's a base in between them, right? So if a carrier crosses the base collector junction, right, it's going to be basically this noise source. Base current, though, has two components, right? It has a component that goes to the base collector junction. That should hopefully be a small one, right? Most of it is going through the emitter. And that's actually a different junction, so it's a completely different event. In fact, the collector current is mostly due to electrons injected from the emitter, not from the base, right? So these are not correlated. They are indeed independent.
So it's not like in MOS transistors where you have a certain amount of correlation between the base and the...
Yeah, very good question. We'll talk about MOS in a moment. There's probably a very small correlation, extremely small, because there are basically some of the collector current is due to the base current injection, but it should be very small because remember it's a reverse bias junction. It's also a minority carrier, so the correlation should be very small. Okay. All right. There's also what we call flicker noise, or some people who are really into the color analogy call this pink noise. Remember the noise, we call it white noise because white light contains all different frequencies in equal amount. So pink noise would tend to have more low frequency content in it, right? Remember, like red is low frequency, blue is high frequency. So if you've got more red, maybe it looks pinkish. Well, flicker noise, if I look at it, most flicker noise has a 1/f spectrum. So in fact, most of the noise power is at very low frequencies because it's rolling off like 1/f. And so this noise source is very self-correlated, very different from thermal noise, which is completely independent from itself. This kind of noise does have this strong self-correlation. It's a very low-frequency phenomenon. And the origin of flicker noise in some ways is not very well understood because lots of different things in nature actually do produce 1/f noise spectrum. Which one in a transistor actually leads to 1/f noise is somewhat controversial. We can basically, in this class, we don't really care where the noise comes from. It's there. We have to deal with it. But we tend to think that it's due to traps. So it's basically, if you build a perfect crystal where there's no discontinuities, no traps, nothing, there would be no flicker noise. But if you have dopant atoms that can capture and release free carriers, because that capture and release process is random, it tends to generate what we call flicker noise. And it turns out that bipolars, BJTs, have much lower, and by much I mean much, much lower, flicker noise than FETs. And we'll talk about that a little bit later, but just to give you a hint, in a FET, you basically have an interface between two materials. So this is the oxide, and basically there's traps inside these oxides, so these are traps, which capture charges from the channel and release the charges back, and so therefore modulate the threshold voltage of this transistor. That generates flicker noise. So that's one mechanism for generating flicker noise. On a bipolar device, though, bipolar device, currents flow in the bulk of the device, right? So here's a quick sketch of a bipolar. The bipolar action occurs under the surface. So the surface is where you don't want to be. So basically the surface has these so-called dangling bonds, incomplete bonds made at this interface, which are the trap sites. If you go deep in the body of the transistor, there are much fewer trap sites, and therefore the flicker noise is much lower. So this is the reason why bipolar devices have much lower flicker noise, and why PMOS devices, depletion PMOS devices in the old days, had much lower flicker noise than NMOS devices, because the channel was actually forming under the surface. All right. So a BJT, let me draw a small signal model. Basically, every physical resistor has noise. So if I draw my equivalent circuit, for instance, RB is a physical base resistance, and therefore there's a noise associated with it. Okay? So then I have R pi. Is there a noise associated with R pi? This must be a really boring lecture. I see two people slipping out, falling asleep. Any noise associated with R pi? No, why not?
Not physical.
Yeah, R pi is a modeling resistor. It's not a physical resistor, right? So R pi doesn't have noise. So the noise is basically the base current noise, not due to R pi. C pi, of course, is a capacitance. It doesn't have noise. C mu also is a capacitance. It doesn't have noise. Then I have my GM generator, and then I have RO. And again, RO, the output resistance of a transistor, is basically not a physical resistor, so it does not generate noise. On the other hand, I do have collector noise. This is the shot noise of the collector. And I have a physical emitter resistance, a collector resistance. That generates noise. And finally, I have an emitter resistance, and likewise, that generates noise. Okay? So the physical noise sources in a transistor are the base current, the base resistance, the emitter resistance, the collector resistance, and the collector shot noise. And you might say, why not? Why can you just use a small signal model? Okay. Well, fortunately, there's one good thing about noise: is it's pretty small. So it's small enough that it will only excite the small signal circuit. You know, if you think about noise in terms of statistics, what's the probability that a noise voltage with a certain RMS, let's say of a nanovolt, will reach 1 volt? Okay? It's probably like the statistics of a bunch of monkeys typing out Hamlet. It's a very small event. Probably won't happen in our lifetimes. Probably not in the lifetime of the universe. So it's a very unlikely event that the noise voltages are going to be large and excite the large signal behavior of this transistor. So at least there we've been spared. We can use small signal models. Okay. How about a FET? Now FETs are a little bit more problematic when it comes to noise. Okay. So again, the physical resistors have noise. So physical resistance, gate resistance, source resistance, drain resistance, right? And these are physical resistors. So again, here's the gate resistance. Here's the source and drain resistance. Here's the channel. Now the gate resistance is a little bit tricky because the current doesn't all flow to the end of the gate and then magically appear in the transistor. Actually, the current is continuously flowing from the gate into the channel, right, through that capacitance. So this is actually a distributed resistance. Okay, and we have to take that into consideration when we calculate its noise. Okay. Now, the other important source of noise is the channel noise. And the channel noise has one important component. There's the thermal noise component. And the other important component is the flicker noise component. Okay. Now the channel noise, because this is basically this channel, this is the inversion layer. You can think of this inversion layer as a nonlinear resistor, right? It's not uniform if you're, let's say, in saturation. But it is a resistor. And we know that resistors generate noise. The only problem is that the amount of resistance depends on where you are in the channel. Okay? It's a little bit more complicated than a simple resistor. Well, if you do the math, you find that that channel resistance has a spot noise that looks like this. This is the channel thermal resistance plus the flicker current. I'll just call this FLK for now and come back to it. So this channel resistance, if we look at these terms, first of all, 4KT GDS0 kind of makes sense. This is the noise current of a conductance GDS0. So if I told you the noise were just equal to 4KT GDS0, you would say, brilliant, I understand where that comes from, because GDS0 is just the channel conductance. Okay? So GDS0 is equal to the channel conductance for VDS equal to 0. Okay? Now, unfortunately, there's this term gamma. And for a long channel transistor, it's equal to 2/3. In some ways, gamma is the correction that takes into account that the channel is not uniform. And the way you calculate gamma, if you guys are into this, you can go home and try this, is you break the channel up into small little pieces. And you say each tiny little piece looks like a resistor, tiny little resistor that generates noise 4KT delta G, where delta G is that tiny little resistor. And then you integrate over all those tiny little resistors to get the total noise current, assuming that they're all acting independently of one another, which is somewhat of an assumption. But at the end of the day, you end up with the total noise being 4KT, the sum of the little g's, and you know the sum of the little g's is GDS0, and this extra factor 2/3. Okay? So GDS0 is equal to the derivative of IDS versus VDS when VDS is equal to 0, and that's simply mu C ox W over L VGS minus VT for a long channel device. Well, it's actually kind of interesting that if you look at the GM of a transistor, so this is basically linear region equation because VDS is equal to 0. This is a saturation region equation to find the GM. That's also given by mu C ox W over L VGS minus VT. Okay? So when people made this observation, they said, aha, that's nice because who knows what GDS0 is anyway? I know what GM is, so I'm going to use GM. So in this equation, for the drain thermal noise, they said it's 4KT gamma GM delta F. Okay? Well, what's the problem with using GM here? Anybody?
Short channel devices.
Exactly. For short channel devices, we define a coefficient alpha, which is the ratio of GM over GDS0, and basically it's not equal to 1, as we see here. This is for long channel. It's in fact less than 1. So some early researchers who used this expression to find the thermal noise of short channel devices came back and found that the noise was actually quite a bit larger, and this was a big problem. Wow, the noise of short channel devices is much larger. They were claiming that gamma could be as large as 4 or 5 instead of 2/3. Well, partly the problem was they were using GM, and they weren't taking into account that your GM drops, right? So that's a part of it. But even if you take into account the correct expression GDS0, you still find that, in fact, so basically before I leave you with this expression, let me correct it and put alpha in there. But you still find that gamma gets larger for short channel devices. Okay, so gamma maybe on the order of 2 is reasonable for a short channel device. And it depends on bias, it depends on how short the channel is. The important point to take away is that treat gamma as a parameter that you get from the process. And don't treat it like 2/3. Treat it as some value that you need to find out when you're doing your design that's going to be larger than 1. Okay? Any questions about the thermal noise of the channel? Yes? I guess the system's screwed up today. Too much gain.
So the channel resistance, it's also not a physical resistance.
No, it is a physical resistance. Yeah. Because a channel is just an inversion layer, right? Think about it this way. When I put my device, let's say a device in linear region. So let me turn the device on. Let me apply a gate voltage bigger than threshold, right? So I form this inversion channel. And then this is the drain, this is the source. And this is just a resistor, right? In between these two nodes. So in linear region, I should mention this. This is for saturation region. For linear region, this is simply a resistor, and gamma goes to 1. Okay, glad you asked that question because I forgot to mention that we were talking about saturation. Any other questions? Yes.
Short channel devices, if you said gamma goes up, is there any specific reason for that?
So why does the gamma go up for short channel devices? Well, part of it is that the thermodynamic equilibrium that we assume that occurs in a long channel device is not really happening in a short channel device. In a short channel device, the average temperature of a conductor could be much higher than the device average temperature. That's because in a short channel device, the fields are very large, and carriers are moving at actually velocities approaching the velocity-saturated velocity. So the average temperature is much higher. So one way to calculate it would be to, actually when you do that integration, instead of taking T as a constant, take T of the actual temperature at that given point in the channel. And that will show that gamma gets larger. Yes? That's right.
But the equation applies to a case of saturation region where VDS is higher than T.
That's right, yeah. So the idea is that once you go into saturation, you have this pinch-off region, right? But this resistance basically is the resistance of the channel. And this is the resistance that's generating noise. And this resistance is approximately, our channel is approximately VD sat over ID, right? Not VDS, because the extra VDS gets dropped across the pinch-off region. Any other questions? All right, these are excellent questions. For now, I'm not going to say too much about the flicker noise because initially flicker noise won't matter. Later on, it'll come back to haunt us. But for now, flicker noise is a low-frequency phenomenon. We usually characterize this with a corner frequency. So the corner frequency is the frequency where the flicker noise is equal to thermal noise. In other words, if I told you a particular MOSFET has a corner frequency of 1 megahertz, that means that if you operate above a megahertz, the thermal noise dominates because the flicker noise has a 1/f spectrum. If you're operating below a megahertz, flicker noise will kill you. Okay? And so first, we're going to deal with circuits that don't perform any frequency translation, like linear amplifiers. So linear amplifier can't take low frequency noise and generate high frequency noise, and so the noise will be dominated by the actual noise at high frequency, and so flicker noise won't matter. Let me give you guys an equation for flicker noise, nevertheless. So flicker noise is highly empirical. In other words, people just go out there and measure the flicker noise and then fit equations to it and not really understand what the origin of the basically all the various coefficients are. So for instance, this is one equation I found, and you can actually find lots of equations. So this is the flicker noise. And it's important to notice a few things about the flicker noise. First of all, it's proportional to the DC current. So DC current goes to 0, flicker noise goes to 0. That's kind of nice. It has the same delta F, this is the spot noise. It's also inversely proportional to Cox and L effective. In other words, if you make your channel length longer, you reduce the flicker noise. If you increase Cox by either increasing W or increasing basically epsilon or decreasing Tox, you also find that the flicker noise goes down. And that's all related to the the so-called pseudo-physics of a flicker noise. Traps, basically if you change the area of your device, you have more. The effect of the traps becomes less of an effect of the overall, let's say, threshold voltage. Again, in this class, I'm not going to go into the details of the physics of flicker noise, partly because I don't understand them, but also for a good reason, because in the beginning of the class, we're going to kind of ignore flicker noise. There's a question in the back.
Is that Cox the effective, or I mean the normalized capacitance, or is it the actual capacitance there at the...
Cox is basically just Tox over epsilon ox over Tox. Yeah, good point. So K, A, and E are determined from measurements. Okay. All right. So given all these different noise sources, we can draw an equivalent circuit for a FET. And again, we use the small signal model for the same reason. There's some gate noise associated with the gate resistance. Remember, this is a distributed noise source, distributed noise. You have C gate to drain, and you might say, what do you mean by distributed? Well, we'll talk about that later, maybe today. Again, you have RO, but RO is not a real resistor. It's a modeling resistor, so it does not generate noise. But you do have the noise of the channel. That's the drain noise. And then again, you have drain resistance, which is physical, which generates noise, and source resistance, which is physical and generates noise. And if you include the body effect in the transistor, so here I'm kind of assuming that there is no body effect, but if you include body effect, then the substrate or body resistance also generates noise through the back gate. Okay? Because there's a resistor, the body node goes to a resistor and then it goes to ground. So that resistance has noise because the body of the transistor is a physical device. And there's a transconductance that takes that noise from the body and turns it into also a drain current. Okay? But for now, the important point when you're doing noise analysis is to focus on the important noise sources, the dominant noise sources. Because noise analysis gets very messy very quickly if you include too many terms. It's much better to let a computer handle hundreds of different noise sources, and when you do your calculations, you should focus on the important noise sources. All right? let me briefly mention the gate noise. So there's the gate physical noise. And this is basically, let's say this is the W of the transistor, this is the L. And this material has some resistance. So basically this is, let's say, poly, and you know its sheet resistance. So you would say, okay, if I know the sheet resistance, then this resistance, gate resistance, should be W over L. No, it should be L over W. Sorry. So let me assume that, let me just draw a transistor to make this more clear. So this is the W of the transistor, this is the L. And current is flowing, let's say, from one contact out here and coming into the transistor. So it should be W over L. Okay. And as I mentioned before, not all the current flows through here, right? If I imagine the current distribution coming through this resistor, it might have something like a triangular shape. So if I plot the current, the gate current density versus W, I know the current has to go to 0 out here, right? So it might have a profile that looks something like this. Okay? In fact, if you do the analysis more carefully, you can analyze this as a distributed RC line, something that we do in 117, for instance. You can analyze this as a transmission line, and you find that the real current distribution is actually exponential. But it's a pretty mild exponential for real resistor, so you know it actually does look pretty linear under the approximations of basically an RC line and a transistor. So I challenge you guys to calculate the loss, the power loss, in a resistor where the current distribution looks like this. Okay? If you do that, what you find is the effective gate resistance is actually 1/3 Rg. Okay. Does that make sense? Is it clear why it should be less than Rg? It's less than Rg because out here there's no current in this resistor, so we're not really putting any power, losing any power here. It's out here where we're putting in lots of current, and therefore here it's peak, here it's 0, and if we take an average value of the effective resistance seen here, we get 1/3. Okay. Immediately then you might argue, well, what if I make double contact on my gate? So here's again, this is a top view of my transistor. So this is my source, this is my drain, this is my gate. If I contact from one side, then I get, this is my W, and this is my L. If I contact from one side, I get 1/3. And I'm telling you the current distribution looks something like this. If I contact from both sides, on the other hand, the current distribution will look something like this. So this is W again, this is W over 2. And if you do the math for this case, in fact, you can apply this result. W goes in half, you have two resistors in parallel. You do the calculation, the gate effective for two contacts is 1/12 the physical gate resistance. Okay? So if you want to reduce the gate resistance of a FET, you can see immediately that you can do two things. You can make the fingers more narrow and put fingers in parallel to build up your transistor, and you can apply double contact to try to reduce the amount of resistance seen through here. And third, if you had a process that had a metal gate, for instance, or if you could put metal on top of this gate, then you would really be doing well, because a metal has a lot less resistance than polysilicon material. And in fact, gas transistors, gallium arsenide transistors, do have metal gates. So they have much lower noise due to the intrinsic gate material. All right, any questions? Now, again, I won't go into too much detail, but there's one more wrinkle that we have to at least mention about FETs. So in a FET, the noise is all due to this, effectively, you know, besides the parasitics, all the noise is really due to this channel, right? But it turns out that a lot of times what we're interested in is the effective noise seen at the gate. So I haven't talked about this yet. We'll talk about it next lecture. Sometimes it's very convenient to what we call input refer this noise. Okay? And the idea is, just like for a resistor, I can say I have a noiseless resistor, and in parallel with it, put a noisy current. I can also take any two-port. We'll see this next lecture. I'll prove this to you guys. That I could take a two-port and make it a noiseless two-port and add what we call equivalent input noise currents and voltages. In fact, let me hold off discussion of this because it's really not the appropriate time. We should first go through the theory of this before I talk about gate-induced noise. But let me just warn you that when you look at your transistor as a two-port, you find that at the gate, the noise is more complicated. And this is due to gate-induced noise. So the intuition behind gate-induced noise is that if I look at this gate, then there's going to be some noise voltage on it. And the reason is because the noise current in the channel can capacitively couple and appear at the gate. Okay? So if I look into the gate of a transistor, ideally you wouldn't expect to see thermal noise, right? You would expect to see the thermal noise of the gate resistance material, but other than that, you wouldn't expect to see any other noise. But in fact, you do see additional noise. And that's called gate-induced noise. Now there's two ways of looking at that. One way is to say, yeah, there's noise in the channel, and some of that leaks into the gate through the capacitance. Okay? The other way to look at that is if I look into the gate of a transistor, I don't see a pure capacitance. We talked about this when we talked about small signal circuits. I in fact see a part of the channel resistance, right? It's a distributed circuit, so it's not easy to analyze, but this looks like a transmission line along the L direction. And so if I look in, there is a real part to the gate resistance, and it's proportional to the channel resistance. In fact, I can show that Z gate is 1 over j omega CGS plus, I'm going to call this Ri. Ri is the effective channel resistance seen at the gate. Again, it's a distributed resistance. And if you do a careful calculation, you find that it's 1/5 times 1 over Gm. And since you see part of that channel on the gate, there's going to be thermal noise at the gate. Of course, this noise is correlated to the noise in the channel because it's the same noise source. It's not a new noise source. It's the channel noise appearing at the gate. So keep in mind that when you look at the gate of a FET and you talk about the noise seen at that port, it is going to contain some of the drain current, and it's going to be correlated to the drain current. Because it's correlated, it makes things a little bit more difficult to handle. But we can handle it. We'll see that next lecture. Okay, we're not done yet. Let me start the topic for next lecture. We still have 5 minutes. So next lecture, we're going to look at noise in a communication system. So next lecture, we're going to take the bird's eye view. Instead of looking at individual components and saying, I have a resistor, how noisy is it? I have a transistor, how noisy is it? I have an amplifier, how noisy is it? Instead of taking that worm's eye view, we're going to take the bird's eye view and say, I have a system, and it's got noise in it. How will that impact, let's say, a communication system? And so how does noise impact a communication system? Well, for instance, in analog systems, like watching a video, we know that this is basically going to give us snow. So if you're watching a very weak station on your TV, you see some snow appear on the screen, right? That's due to noise. If the signal is too weak, you see that. If you're listening to audio, what you see is you hear some static, you hear some background noise. In fact, if you guys have ever listened to an album as opposed to a CD, it's very interesting. You hear quite a bit of noise. That's because the system inherently has a lot of noise built into it. Now, today we're kind of, these are the old analog systems. Today we have digital communications. And one of the big reasons for using a digital communication system is the inherent noise immunity. In other words, if you guys know from your digital electronics classes that as long as the noise is smaller than the noise margin, you won't get a false transition, right? So that's great. It seems like in a digital system, as long as the noise is low enough, you wouldn't actually ever have a problem. No, it's not quite so good. As we'll talk about next lecture, when you have noise being added to your signal in a communication system, every once in a while you get unlucky enough that you do get basically false detection of what bits were sent. So in a digital communication system, noise leads to what we call bit error rates, BER. And so we find that based on, now bit error rates are fine, we can handle them. We can have coding in our system, we can detect when they occur, and we can have retransmissions, and we have whole complicated networking algorithms all built to deal with bit errors. But the more we get, the harder it is to correct for them. So next lecture we're going to talk about where bit errors come from, and then talk about how the noise of the system impacts the ultimately the bit error rate of the communication system. Okay. Any questions up to here? Okay. If you guys came in late, a couple of announcements. Homework is next week, next Tuesday. And please pick up your homework today.